Okay, good morning, everyone. Uh, Today, we are going to talk about Chapter 13, Robot Motion Planning, and we are going to learn a notion named Minkowski sums to deal with polygonal robots that are trying to find their way in an environment 2D on a 2D map where the obstacles are also polygonal obstacles. All right, so the motivating problem in these last 2 weeks that we are going to talk about. So the last two chapters that we are going to discuss in this course are chapter 13 and chapter 15. On chapter 13, we are going to talk about robot motion planning, and our goal will be to find. So let me zoom in on this. Given a robot in an environment where the objects are static, they're not moving, uh, given a start position for our robot, our goal will be to plan a path to a target position on this 2D map. And in this chapter, we will not be concerned with finding the shortest path. Finding any path will be sufficient for our purposes. And we will, the main thing that will be introduced in this chapter is to some terminology in robotics, like the configuration space, and what happens instead of having a point robot when we have a polygonal robot. How does the configuration space changes? So the notion, terms of workspace, configuration space, these things are introduced. And since this is really not a very recent book. I mean, this the book that we are using in computational geometry. Our textbook is a very classical and still a book that is used in computational geometry. But it may be a little bit outdated if you're really interested in the area of robotics. The notions that are discussed here may be some introductory classical terminology that robotics needs, but I'm not a researcher in the area of robotics, so I don't know the latest developments, but I'm sure there are lots of developments, especially concerning AI, computer vision, and things like that, or reinforcement learning. So really, it's a learning problem. Lots of computer vision is involved. But in this course, the last two chapters, which are we will discuss, they're about the motivating problems are about robotics, but we will just turn them into geometry problems, computational geometry problems in 2 dimensions. But still, it will be a nice introduction if maybe you may be interested in this area, and it will be nice to hear some terminology from a different perspective. Okay, so the motion planning. So this chapter is specifically talking about the motion planning aspects of robotics, and our goal will be to plan a path in an environment. As I said, this is the general problem is maybe very complex. There may be moving objects around, but we will make lots of assumptions, and we will just forget about the three-dimensional aspects of our environment. We will just assume this basic problem where we have a 2D floor map given to us as as a list of polygons in the are obstacles in the environment. So the obstacles will be given to us as non-intersecting um, obstacles like this. They may touch each other at the boundaries, but the obstacles will be polygons that are not intersecting. If two obstacles intersect, I mean, in 3 dimensions, they may be on top of each other like this. We will just represent them as as a single 2 dimensional polygon. As you can see, the obstacles are not necessarily convex. We can handle non-convex obstacles, especially if you're going to deal with non-convex obstacles in the next week. In next week, when we talk about the finding shortest path in such a map, we will have non-convex obstacles. This week's chapter is mostly focusing on what will happen instead of having a point-like robot when we have polygonal robot, how does our free space change. So if the white regions here are the parts of the workspace where the robot is free to move, but the robot is not able to go inside, collide with the obstacles. The robot is allowed to touch the obstacles, so they may touch, the robot and the obstacle may touch at the boundaries, but it's not allowed to. The area, the intersecting area of the robot's polygon and a particular obstacle should be zero. That area should be zero. They should not have a non-zero area intersection between the robot's polygon and the obstacle polygon. So first, we are going to think about how we can represent different positions of the robot or rotations of the robot, which we call a specific configuration. So the robot, for example, at a resting position will be defined, the robot's polygon will be defined as a set of vertices, just like any other polygon. But when we want to move this robot to a particular position, I mean, if you are taking the computer graphics course, there will be these will be like transformations for the robot. We can translate the robot to a particular position. So we can have the translation in 2D could be specified by two parameters, tx and ty, and we can have these two parameters, for example, from a resting position. This lower left corner of this figure may be 0, 0, and we may identify the vertices of our robot at this with respect to this 0, 0, and this may be also our reference point at the resting position. Moving 0, 0 to tx, ty also will mean that moving all of the vertices of the robot to that polygon. So a certain positioning of the robot in this environment could be indicated by two parameters for just a translational robot. If the robot is also allowed to rotate in 2D, in 2D, the rotation, we are just going to assume the robot rotates around its center of mass, for example. We are not going to talk about rotation. I mean, this chapter does not talk about rotation around a particular pivot point or so. The pivot point is always the same. We just deal about, for example, considering the polygon of the robot. Maybe rotating it slightly will help you pass through spaces, certain spaces. So that rotation could actually be indicated by a single, I have it somewhere here, like this, yeah, by a single angle in 2D. So this may be a particular configuration, 6445. This is my robot's polygon in this resting position, and this 6445 may indicate that the robot has moved 6 units to the right, 4 units to the top, and it's rotated in such a way that its bottom edge makes 45-degree angle with the x-axis. So this may be a particular configuration. All right, now this is how we are going to represent our robot's movement by and the robot's movement in the scene will be a sequence of configuration changes. The configuration, actually, when the robot is moving in an environment, the configuration change may be continuous. But when we're planning a path, it's really not good to plan something. I mean, it may be difficult. We may still do that, but planning something continuously is difficult. I mean, think about how you find shortest path on a graph. Do you jump from node to node? So we have discrete steps for it. And when you're planning something, the plan usually is comprised of a sequence of discrete steps. You will instruct the robot, go from here to here, then go from here to here, go from here to here, change your rotation to this angle, do this and do that. So these sequence of instructions, as you can see, are finite and they're discrete. So therefore, our plan, our roadmap, will be a sequence of discrete steps when we're planning a path for the robot. Although the configuration space itself maybe, I mean, the configuration space is a continuous space. We can have any in any position. So what I mean is that these values here, 6, 4, 45, they can be any real number. So these are continuous. The configuration space is continuous. This can be any angle, a floating point number here. But when we are planning, we will give the robot a discrete sequence of instructions, and therefore our path, the path that we planned, will be a curve, a piecewise linear curve in the configuration space. What does it mean to be a piecewise linear curve in the configuration space? It means that, for example, each for example, here the workspace here is a two-dimensional workspace. We have a 2D map, we have a 2D polygon, but if you look at the configuration, the robot can have tx, ty, and then phi angle. This configuration space itself is three-dimensional. It's not necessarily Euclidean, because although the x and y coordinates may be between minus infinity and plus infinity, this angle is restricted to values between 0 and 360, and therefore it's more like a cylinder type of, it's the space, if you try to visualize the space, it may be something like that. But in three-dimensional robotics, for example, it's very difficult to visualize the configuration space, because you may have a 6 degree of freedom robot in which the movement can be the configuration of where the position, the robot's current position may be indicated with 3 values, x, y, z coordinates, and the orientation of the robot in 3 dimensions may be given with Euler angles or pitch, yaw, and roll angles, which are 3 angles. So in 3 dimensions, you can specify the certain particular orientation of an object. Okay, the object may rotate like this, it may rotate like this, or so this is the pitch, I think. No, is it roll? I don't know the terminology. So I know this is roll. Okay, the roll angle. I think this is pitch and this is yaw. Okay, so these 3 angles will give you 6 degrees of freedom, which means that the configuration space in 3 dimensions is a 6-dimensional space. So we cannot even visualize that 6-dimensional space. And our roadmap, our instructions to the robot will be jumping from one 6-dimensional point to the other. So from one configuration to the other, from one configuration to the other. So it will actually be a path. I think I have also an example here. Yeah, this example will suffice actually. If you look at this one, this was the starting position. Configuration, change the configuration from this to here, then from this to here. So from one configuration to the other, it will be from one 6-dimensional point to another 6-dimensional point. It will have a starting point, it will have an ending configuration, and between these things we will have a curve in 6 dimensions, which is comprised of points in between. So between every 2 specific configuration, we just draw a line segment, and it becomes a piecewise linear curve in the configuration space. And you can actually, sometimes you may not want your robot to do some abrupt changes at these junctions, at these configuration changes. You may even turn it to a continuous plan by fitting a continuous curve in 6 dimensions. This is possible. For example, you could have I mean, we haven't learned this in computer graphics yet, class yet, but we're going to learn about cubic curves or quintic curves, so that we can actually fit a continuous smooth curve to a piecewise linear set of control points. And we may give that also as a plan to the robot. Actually, I told you that it's difficult to give instructions that are continuous, but after we plan something that is discrete, we may turn it into a continuous plan by fitting a spline on top of it. Okay, so it's possible. But here, the organization of this chapter is like this. We'll first talk about this terminology. I already started doing that. The configuration space, the workspace of the robot, uh, and so that's the first section. And then we are going to simplify certain things. We're the simplest setting where we try to plan a path for a robot is where the robot is point-like. So the first is when we have a point robot with no polygon, just if it's just a point. How do you plan a path in an environment where there are obstacles? We first see how to solve it by using trapezoidal maps, and then we are going to extend this initial problem into the case where the robot is no longer a point, but it's a convex polygon. And we are also going to assume the obstacles are convex objects too, to see the resulting the resulting configuration space will be linear if we have both the robot and the obstacles as convex polygons. And then we will solve this problem by the main thing in this chapter is how the configuration space is going to look like when we have a polygonal robot, and how do we compute that configuration space. So if you have polygonal robot, so it's right here, let me show you. So if you look at this, this is the difference between of the workspace and the configuration space when we have a point, when we have a polygonal robot. So this is, if you, the workspace is the physical space where we have physical obstacles that do not intersect with each other. We have a polygonal robot, and this is how we see with a camera, with this is the real physical workspace. Now, configuration space, as I said, is the space where we have we can set these tx, ty, the translation parameters or rotation parameters of our robot. In the first case, we're just going to also again limit ourselves to translational robots to see also to visualize the configuration space also as a 2D map. When we have a translational robot, the only parameters are tx, ty, and that tx, ty here, it's like getting from this workspace to configuration space is like changing your robot to a point-like robot, because you can represent, due to this reference point, any configuration of your robot for a translational robot can be indicated by just two variables tx, ty. That tx, ty becomes a point in this configuration space. So it's like converting your problem from a polygonal robot to a point-like robot, but this time you need to, as you can see, the configuration space is not the same as your workspace. Okay, the main point in this chapter is how do we compute this configuration space when we have a polygonal robot. Look at these shapes. They are like polygons, okay, but it's like the original workspace obstacle is expanded to account for the case that this reference point inside the robot cannot, I mean, if the reference point cannot come to here, because in that case the robot's polygon is going to intersect with this. So if you look at this, it's no longer a triangle. It's something, the number of vertices in this configuration space obstacle is determined by the robot's polygon, the number of vertices in the robot's polygon, and the number of vertices in the obstacle themselves. But how do we compute this shape around this polygon is the main thing that we are going to learn today. And for that, we are going to learn a notion called Minkowski sums. So the space around this polygon actually is the Minkowski sum of the workspace obstacle with the reflection of the robot's polygon around origin. So it's not actually directly P plus R. If the polygon here is P, it's not P Minkowski sum the robot's polygon directly. It's the inverse, it's like minus robots polygon is what we're Minkowski summing this. And I'm going to show that theorem has a very short proof. I'm going to also go over that. But I hope you understand the difference between workspace and configuration space. In configuration space, you may think that this is not actually the robot. This point that you see in the configuration space is a specific configuration of txty. If our robot was also a rotational robot, if it's allowed to rotate around itself, this configuration space will be three-dimensional. It's not only, we will not be able to visualize it like this. All right, so each point here in this configuration space refers to a particular specific positioning and orientation of our robot. And our goal will be, again, to find a path. This is our plan of configuration points, and this configuration space has some white regions, which are configurations that we're allowed to make, and the obstacles that appear in this configuration are like the forbidden configurations. We cannot have our robot to have a configuration that is inside this shaded region, because that configuration results in a collision of our obstacle, of our robot with some obstacle. All right, so this is the free space, free configuration space, free, and the forbidden configuration space. So this is the distinction between workspace and the configuration space. Now let's see if I'm missing anything. By the way, if you have any questions at any time, please feel free to stop me, or if you have also any comments, things to add. If you have taken a robotics course, it would be good if you figure out certain differences between this course and the robotics course. For example, you may say, oh, in robotics, we actually tell this not the configuration space, but we tell it, we name it like this, or it will be good to provide analogy between these two things. As I said, I don't give a robotics course myself, so I'm really not familiar with the up-to-date terminology in this area. Okay, now now we can actually directly go ahead and solve our first problem. If the robot was a point-like robot, how do we find a path in an environment like this, on a 2D map like this? So we can now go to our section 2, in which we are going to find a path for our point robot. By the way, so let me also talk about what this figure is about. This figure is basically saying that although the workspace obstacles are not intersecting with each other, when we expand them to account for polygonal robots in the configuration space, the configuration space obstacles, the expanded polygons, may actually intersect with each other, which will indicate that there is no free space in between them. The robot cannot fit through this region between these two obstacles, and it's indicated. So they may intersect. So we may need an additional algorithm after we not just expanding these polygons will not be sufficient to find configuration space obstacles. We may need to merge them together to form these polygons. Okay, so actually the book also talks about an algorithm to do just that. But we will also see something really interesting when we have these expanded obstacles. When the robot is a convex object and the obstacles are also convex objects, the expanded, their Minkowski sum, is a very special type of polygon. Topologically, they are called pseudo-disks. They behave like disks, circles. Because a Minkowski sum, one Minkowski sum, another Minkowski sum, can intersect with each other at most, if both of them are convex, by the way, at most 2 points, just like circles. So we will use this observation to prove that the final configuration space, its complexity, will be linear. It's not going to, not all the obstacles are going to intersect with each other in complex manner. They will intersect with only at a certain, the number of crossings between them will only be a certain number of times, and it will be linear in the number of obstacles we have. So we will also talk about these interesting properties of these expanded polygons, which are, we are going to define Minkowski sums. Okay, so let's go ahead and start with the second section, a point robot. So when we have a point robot, what happens is that the workspace is exactly like the configuration space. So there's no difference between the workspace and configuration space when we have a point robot, because wherever you can take your point robot in the workspace, that configuration, that particular configuration, will also apply to your point in the configuration. So basically, there is no distinction between workspace and configuration space, and if you have a point robot. Now, how can we find the path from, so here, these are my obstacles. The free configuration space will be exactly the same as the free environment in my workspace. And in order to have some bounded free space, because we are going to build some kind of a structure on top of this in order to find a path from a starting position to an ending position, to a goal position. And we are going to do that since this free space is continuous. We don't finding paths, planning paths is really difficult. I mean, to in a continuous space. So our goal will be, actually, the first thing we'll do is we're going to build a graph, a discrete structure with some nodes and edges. We'll build a graph on this free space, which will allow us to use graph traversal algorithms like breadth first search, or we can also use Dijkstra's shortest path algorithm to find a path from some start node to some target node in this discrete structure. Okay, so but in order to build a trapezoidal map on this, we also first bound our free space with a box. I mean, this may be actually the boundaries of our room. So our robot is, we assume that it's in some kind of a rectangular room. So we bound the free space with this bounding box, and we have obstacles within the workspace, which are polygonal obstacles. And uh, the solution we are going to do is we are going to build a trapezoidal map on the edges of these, using the edges of these polygonal obstacles. We first build a trapezoidal map, and it looks like this. So this is our trapezoidal map for the workspace and configuration space that you have seen. And if you look at this, certain trapezoids are actually irrelevant. We are not interested in the trapezoids that are within the obstacles, because our point robot is never going to go inside the obstacles. So we actually delete the trapezoids that are within obstacles. And this can be established by writing code to determine whether a trapezoid is inside or outside an obstacle. We know the edges of all these polygons. We know how the edges bound the inside of the obstacle. So if a trapezoid is also bounded by the same edge, we can actually just delete that trapezoid from our doubly connected edge list. So the trapezoidal map will be at the end given to us as a doubly connected edge list with trapezoids as the faces. We will have edge records, which are about the boundaries of these trapezoids. We will have vertices, but we post-process this trapezoidal map to delete the trapezoids that are within obstacles, because we don't want to deal with them. We don't want to we don't want to put some nodes related to these trapezoids to our graph that we are going to construct later. And therefore, after post-processing, the trapezoidal map is converted to this one. Another interesting thing here is that we are going to use this trapezoidal map, but we are not going to use the search structure. You know, we also, if you remember in chapter 6, we, along with the trapezoidal map, we were building a search structure. That was your third assignment, so you have worked on it recently, so you know what that search structure looks like. And the search structure allows you to search a particular point on your map in sublinear time, expected all-again time. But since we are going to try to find the path, in this case, we are not going to perform many point location queries in this particular problem. We are not actually interested in sublinear time locating of a starting position or an ending position, because while we are finding the path from starting position to end position, we are already going to spend time that is linear. Okay, so the overall complexity of the algorithm is linear, so the one component being sublinear does not actually help much. All right, so therefore the search structure of the trapezoidal map for this specific problem, you don't need to build that search structure. Just get the trapezoidal map with the vertical extensions, and that's it. Don't build a search structure for this particular problem. Okay, so after we have this, we now build a graph on top of this. By the way, I want to again remind you that in this chapter, our goal is not to find the shortest path from the start position to goal position. Our goal is to find any path, because if you want to find the shortest path, this graph that we are going to build on this trapezoidal map is not going to help to find the shortest path, because it will be just a graph which can actually the path we find on the graph nodes could actually be made shorter with the different configuration configuration space curve. All right, so here is what we are going to do. So this is the graph that we're building. The graph that we are going to build is like this. So here are the rules. So we have the trapezoids themselves. You see the dashed line segments here are the edges of the graph, and the book's terminology, or in graph theoretic terminology, they're also called arcs. An arc between two nodes in the graph, or I simply call the vertices and edges. Okay, if I have a graph is nothing but a set of vertices and a set of edges. The dashed line segments are your edges, and these hollow disks, these are the nodes of your graph. And here is how we determine our nodes. For every trapezoid in our trapezoidal map, we have a node. And these nodes also, I mean, the graph itself is a discrete structure with no layout actually, but we also give xy coordinates to these nodes, because at the end these xy coordinates will be our plan in the configuration space. We will have to say, we'll tell the robot move from here to here. So this graph is not only a set of vertices and edges, the vertices also have some planar embedding in the 2D space. They have a 2D coordinate. And for the nodes that we add for every trapezoid, then we just place these nodes at the centers of the trapezoid. Okay, we can just compute the middle point between its bottom edge and top edge, and also its right edge and left edge. So if you remember the trapezoidal map, every trapezoid has two vertical boundaries on the left and on the right. And it may be the case that the vertical boundary may be a single, either two vertical boundaries on the left and right, or a single boundary either on the left or right. In this case, our trapezoids will be like a triangle, a degenerate trapezoid. In this example, there is no such trapezoid. Every trapezoid have exactly two left and right vertical edges. Um, but some of them can be, I mean, if you look at this trapezoid, it has two left edges, which are because at the center we have this vertex of the obstacle, so there's one extension to the top, the other extensions to the bottom, so we have these vertical extensions. So we have nodes at the centers of trapezoids. We also place nodes at the middle, at the center of each vertical extension. Okay, these edges, these vertical edges that we extend from every vertex, this one and this one, we also they are indicated in our edge records. While we're building the trapezoid, we have these vertical extensions are done, and therefore for each vertical extension we also insert a node to our graph, and we place that node, its planar embedding is going to be the center of that vertical extension. So we have this many nodes, and if the number of obstacles is n, I mean if the number of vertices of the obstacles is n, our graph will also contain linear number of vertices. And how do we now we have determined the vertices of our graph. How do we determine the edges of our graph? From the edges are always between a trapezoidal node, a trapezoid node to an edge node, or to a vertical extension node. So if the vertical extension is incident on a trapezoid, we just put an edge between its node and to the trapezoid node. So the edges are between, as you can see, trapezoid nodes to edge nodes, to edge node to trapezoid node to edge nodes. This will ensure that since trapezoids are convex objects, this will ensure that having these edges changing from this configuration to this configuration will make sure that we are still in the free configuration space. We are not colliding with any obstacles because we are inside a trapezoid, moving from any point inside the trapezoid to one of its edges. It's collision free. And from that edge, if you move to the adjacent trapezoid's center, again, it's collision free. We may not guarantee the same thing between two neighbor trapezoid centers. Okay, for example, if you try to go from this trapezoid center directly to the other trapezoid center, as you can see, it may not be a collision-free path. It may intersect with an obstacle. Therefore, we cannot do that. That's the reason we have these vertical extension nodes in our graph. They are like hub points, hub nodes to allow us to move from one trapezoid to the other. Okay, so this becomes a graph with the defined edges and the nodes in the graph. It becomes a graph that will allow us to move in the configurations space in discrete steps. Okay, now therefore, as you can see, the way it's constructed, it will never guarantee the shortest path. For example, if I want to, this is my start position, this is my target position, the way you are going to move that to that position is move here to here, here to here, and then here like this, or maybe directly from here to here. But as you can see, it's not going to be the shortest path. The shortest path, if you're interested in the shortest path for your robot, you'll see that this graph doesn't help. You need to build a graph in which the vertices of the polygons are actually the nodes. Okay, so that's going to be something interesting, which we'll see next week. Next week in chapter 15, we are going to build a different graph for planning, which is not going to be like this. That graph is going to contain the vertices of the polygonal obstacles as the graph nodes. And our goal will be to find from a vertex of a polygon which other vertex can I go directly. We'll try to compute free line of sight vertices, which is called the visibility graph. We will compute the visibility graph next week. That's next week's topic. So this week, all our main goal is just to find the shortest path. Not the shortest path, any path. Sorry, this week our goal is to find any path from a started position to an ending position. And the algorithm is going to be like this. Given a starting position, let's see. Let me just copy this to GIMP and try to actually draw something while I'm talking about it. All right, now let me also change the color to red. All right, so if we are given a starting position, for example, I want my point robot is going to start from here, and it's going to, this is the target location. I want my robot to go from here to here. So what we're going to do is this. We are first going to find the trapezoid that contains this starting position. So this is start, this is target. Find the trapezoid that contains the start and find the trapezoid that contains the target by going over all of your trapezoids. In linear time, you can do that. This is why I told you that we don't need the search structure, because we can go over all the trapezoids in ON time to find which one contains S, because we are already going to spend ON time to traverse this graph that we constructed, so we will never reach sublinear time during planning. And therefore, we can as well find the start and target nodes also in linear time by going over all of the trapezoids, which one contains S and which one contains T. And after that, after we find this trapezoid, we also may have links. We know the center node of this trapezoid. We know the center node of this trapezoid. We run a breadth-first search from this starting node. Let's call the start node here VS, and let's call this node the target node in our graph. So in our graph, we run a depth first, or not depth first, sorry, breadth first traversal, because breadth first traversal will ensure that you find a path from VS to VT in minimum number of hops. A path, a simple path on this graph with minimum number of edges on this path, minimum length path will be found. And each of these edges, they are treated as length 1. We do not use these are not weighted edges. We do not use the Euclidean distance from this node to this node to give weights to these edges. They're just counted as 1, because the reason is that we're not interested in the shortest path anyway. So why bother giving weights to these arcs, to these edges? So starting from this VS, how do you run breadth first traversal? You first visit its first neighbors. You use a queue. For example, all of its neighbors are inserted into the queue and marked as to be visited. Okay, and then they're visited next, and their level is 1 plus. For example, if this is our starting node, which is at level 0, all of its neighbors are going to be at level 1. And when I visit these, I also insert their unvisited neighbors to my queue, and which will be at level 2. And from this level 2, so I just expand my graph by visiting all of these nodes like in breadth first manner, like a wave, a circular wave propagating on the plane. It's something like that. And after that, I'm going to reach this if there's a path. If first of all, if my graph is connected, there will always be a path from VS to VT. But it may be the case that the graph is not connected. Imagine there's an obstacle right at the center of the room, which this allows you to go from the left side of the room to the right side of the room. In that case, we will have a graph which is not connected. So it may not be possible to go from one node from here to another node from here to here in here. So therefore, the path with breadth first traversal sometimes may not exist. In that case, we will just report to the user that there's no path from your starting position to your target position. So after we find our path, for example, it may be this. Actually, it's not this. Probably the shortest, the minimum number of hops will be something like this. Okay, so after we find our uh, path on the graph, we just connect VT to T because they're on the same trapezoid. It means that the line segment that connect VT and T is in the free space. We also connect VS and S, it's also in the free space. So this becomes our plan for a point-like robot. So this is the algorithm that we're going to use, and the algorithm is the number of edges in the graph. Since it's a planar graph, it's also linear. There are no edge crossings. As you can see, the way we define uh, the edges do not cross each other, so it's a planar graph, and which means that the number of edges is also linear on the number of nodes we have here. So the breadth first search takes OE time, the number of edges. Since the number of edges is linear, we can find a path from VS to VT in linear time. And the construction of the trapezoidal map takes, I think, O(n) log n time, so that the final theorem about this section is in O(n) log n time, we construct the trapezoidal map, and after we have the trapezoidal map, we can find, so this is the theorem 13.2. If we have a point robot moving among a set of polygonal obstacles with n edges in total, we can preprocess S in O(n) log n expected time and build a trapezoidal map. And after that, we find the path between a start and a goal position in this free configuration space in linear time by using breadth first traversal. The pseudocode of the algorithm is here. And it describes exactly what I just told you on that figure. Okay, you can take a look at it if you want, but it's just the main thing is the path is found by using this breadth first traversal from V start to V goal on this graph we call the graph of the roadmap, which is a discrete graph of set of vertices and edges. All right, and actually the proof of correctness is trivial. It's really the algorithm itself is really intuitive, and we are going to talk about next the Minkowski sums. Okay, the Minkowski sums, the next thing we are going to do is extend this point robot into a polygonal robot and see how the configuration space is going to change with this extension. But I think it's a good time now for a break, okay, before we start on section 13.3. So let's have a 13-minute, 12-minute break until 10:40. So I will stop the meeting now and stop the recording now, and we will meet at 10:40 in 12 minutes.